Previously, we have discussed about the concept of delta modulation, and we saw that delta modulator is a 1-bit quantizer, which means that the output of delta modulator can change only one step at a time. It cannot make a switch of multiple steps in one go. It can switch only one step at a time. It can go either one quantization step up, or it can come down one quantization step, and hence we call hence delta modulation is referred to as a 1-bit quantizer. And we also discussed about the two possible distortions that occur that can occur in delta modulation. One is the slope overload distortion, which occurs when the slope of the signal is large. That means when the signal is changing rapidly. So in this case, the slope is large, and in such a case, the output of the delta modulator is not able to follow the signal very closely. If you see here, the signal is dropping here, but the delta modulator output is not changing as quickly enough. So that situation here is called as slope overload in delta modulation. So that's here. That's the slope overload part. Okay. And that happens when the slope of the input signal is large. Okay. And the second type of distortion that happens in delta modulation is what is called as granular noise, which occurs when the signal slope is almost zero, when the slope is very small. So that means the signal is more or less constant, and in such a scenario, the output of the delta modulator keeps oscillating between two quantization levels. So this is called as granular noise. Okay. The focus of today's lecture is going to be slope overload noise, and what can we do in delta modulation to avoid slope overload noise. So the focus of today's lecture is to find what we call as the condition to avoid slope overload in delta modulation. Okay, so and then later on we will also compare this condition with the similar condition that we derived for differential pulse code modulation, and see which of the two, that is DPCM or DM, requires a higher sampling frequency in order to avoid slope overload. Okay, and the procedure is going to be quite similar to the procedure that we followed in differential pulse code modulation. So we want to find out what is the maximum slope of the delta modulator output, and we need to ensure that the condition that must be satisfied is that the maximum slope that the delta modulation system can support should be at least the maximum slope of the input signal. If this condition is satisfied, then the slope overload problem can be avoided. So we want to find out what is the maximum slope of the delta modulation system. So as you know, slope is dy by dx, right? So we want to find out what is the maximum step change along the y-axis and what is the maximum step change along the x-axis. So that would give us the maximum slope for the delta modulator output. So let's write down maximum step change along the x-axis is the sampling period Ts equals 1 by Fs. So we are moving one sample at a time, right? Because it's one sample and the next sample and the third sample and so on. So the maximum step change along the x-axis is the sampling period Ts, which is the inverse of the sampling rate or sampling frequency Fs. So Ts is 1 by Fs. That's the maximum step change along the x-axis. Similarly, the maximum step change along the y-axis in delta modulation is 1 delta. So each in each sample interval, the output can go up by 1 step size or go down by 1 step size. So the maximum step change along the y-axis is plus or minus delta. It can go up 1 step or go down 1 step. So that distance here, that distance between two quantization steps is quantization levels, is the quantization step size delta. So we are interested in finding the magnitude of the maximum slope. So that's dy by dx. We want to take the magnitude and take the maximum value. So that will give us dy by dx, which is dy is delta. So since we are interested only in the magnitude, and the maximum value is delta, and similarly the maximum step change along the x-axis, dx is ts. So that is delta divided by ts is 1 by fs. So we can write that as fs delta. So that is the maximum slope that the delta modulator output can support. Now we want to ensure that this maximum slope of the delta modulator output is at least the maximum slope of the input signal. In that case, we can avoid slope overload distortion in delta modulation. So to avoid slope overload, this term fs delta should be at least the maximum slope of the input signal, which is the derivative of the input signal m of t, and we are interested in taking the maximum magnitude of that derivative. Okay, so if this condition is satisfied, then the slope overload would be avoided in delta modulation. So let's take an example, a simple example of a single tone sinusoidal signal as our input signal, m of t. We'll say Vm sine 2 pi fmt. Then we will have the derivative of this d by dt of m of t will be 2 pi Vm fm. The derivative of sine is cosine 2 pi fmt into 2 pi fm. So into 2 pi fm, I've written that 2 pi fm here, okay, along with this Vm. And then from this we can take the peak magnitude. So d by dt of m of t magnitude maximum value is simply 2 pi Vm fm. Okay, so in order to avoid slope overload for this particular example, okay, for this particular example input signal, which is a very simplistic signal, the value of fs into delta should be at least 2 pi Vm fm, or in other words, the sampling rate fs should be at least two pi Vm fm divided by delta. So that's the condition that must be satisfied in order to avoid slope overload in delta modulation. So we'll compare this now with the similar condition that we derived for differential pulse code modulation and see which of the two requires a higher sampling frequency or higher sampling rate to avoid slope overload. So let's recall. For differential pulse code modulation, the condition to avoid slope overload was fs is Fs should be at least 2 pi Vm Fm by L minus 1 times delta, right? So that's at least, right? This is for dPCM, and just to make a distinction between the Fs value for dPCM and for dm, I'll write it as Fs, and in brackets I'll write dPCM. Okay, for dPCM, this is the minimum sampling rate that is required to avoid slope overload, and the corresponding sampling rate required for delta modulation should be at least 2 pi Vm Fm by delta. Okay, where delta is the step size, and this applies to, okay, both of these, they apply, or these equations are based on m of t equals Vm sine 2 pi Fmt. It could also be cosine, right? Even if it is cosine, we'll get the same answer, because when you differentiate the cosine and take its peak magnitude, you will get the same 2 pi Vm Fm. Okay, so this condition applies when the input signal m of d is a simple single tone sinusoidal signal. Single tone means it has only a single frequency component, which is Fm, okay, F subscript m. Now if you compare these two conditions for the sampling rate, when would these two be equal? When would these two right hand sides would be equal? These two would be equal when L is equal to 2. When the number of quantization levels in dPCM is 2, then we'll have 2 minus 1 is 1 times delta, which is the same as this, because the numerator is the same here in both the cases, 2 pi Vm Fm. The only difference is here, this factor of L minus 1 in the denominator for dPCM. And these two expressions on the right hand side would be equal when the number of quantization levels L is equal to 2, right? But in practice, usually the number of quantization levels is going to be more than 2. So it could be 8, 16. If it's like speech signal, it's going to be like 256 quantization levels, and so on. So what we understand is that because there's a number here in the denominator for differential pulse code modulation which is greater than 1, that means this term here, let me mark it, what I'm circling in red, okay, that is exactly what we have for delta modulation. So we can write this as the sampling rate for dPCM is the minimum sampling rate required in dPCM for avoiding slope overload is equal to the minimum sampling rate required for delta modulation divided by L minus 1, right? And since L is usually going to be greater than 2, that means the sampling rate for dPCM, so it implies that the sampling rate required for dPCM is less than the required sampling rate for delta modulation to avoid slope overload. Okay, to avoid slope overload. That means in delta modulation, to avoid slope overload, you need a much higher sampling frequency as compared to differential pulse code modulation to avoid slope overload. Okay, so, and it is the sampling rate in delta modulation is going to be larger by a factor of L minus 1. So in delta modulation, the sampling rate let me be specific, the minimum sampling rate required to avoid slope overload is greater than that of DPCM by a factor of L minus 1. Okay, or conversely we can say that DPCM or the sampling rate required for differential pulse code modulation is smaller by a factor of L minus 1, or for delta modulation it is greater by a factor of L minus 1. Okay, so that's the comparison between the required sampling rate for avoiding slope overload in differential pulse code modulation and delta modulation. And we clearly see that the sampling rate required in delta modulation is higher by a factor of L minus 1 as compared to differential pulse code modulation. We will now do an example where we will have more than a single tone. Rather than using a simple signal which has only a single frequency component, what if we had this M of t, this input signal, which was a sum of multiple frequency components, and then we will try to determine the minimum sampling rate required to avoid slope overload for both delta modulation and differential pulse code modulation, and try to figure out what the what difference is there between the two of them. Okay, we will do an example for that now. So let us now consider this example where we have a signal M of t which is consisting of two frequency components. One is 10 Hertz, the other is 20 Hertz. It's 2 pi ft, right? So if you take the 2 pi separately, the frequency value is f equals to 10, and here f equals to 20. So I'll just multiply the 2 pi and f together and written as 20 pi and 40 pi respectively. Okay, so this M of t is a sum of two frequency components, and we want to find out what should be the minimum sampling frequency for these for this signal if applied to a delta modulation system and a differential pulse code modulation system, given that it has a certain step size delta and a certain number of quantization levels L, which are same for both the DM and DPCM. Okay, so let us evaluate what should be the minimum sampling frequency for both these cases. So we have this M of t. The first thing we need to do is we want to find the slope of this. So d by dt of M of t. So we want to differentiate this. So it will be 6 into differentiation of sine is cosine 20 pi t into 20 pi, right? Because derivative with respect to t, plus 4 derivative of cosine is minus sine, that's 40 pi t into 40 pi. So that will be, so we can bring this 20 pi and multiply it with the 6 here. So 20 into 6 is 120 pi. So 120 pi cosine 20 pi t, and we have plus into minus, so this will become minus. So minus, we can multiply this 4 with this 40 pi, so that will make it 160 pi into sine 40 pi t. So that's the derivative of the input signal M of t. Next, we are interested in taking the peak magnitude d by dt of M of t, and we want to take only the magnitude of this, and we are interested in the maximum magnitude. So the peak magnitude of this first term, the cosine term, is 120 pi, and the peak magnitude of the second term, which is the sine term, is 160 pi. And because we are interested only in the magnitude, we don't need to worry about this minus sign. So it is the peak magnitude of this combined term of this summation here would be 120 pi plus 160 pi. Okay, that would be the peak magnitude of this derivative. So that would be 120 pi plus 160 pi, which is 280 pi. So that's the maximum slope of the input signal, and we get it as 280 pi. Now we have for delta modulation for DM, Fs delta should be at least d by dt of m of t magnitude maximum. Right? So in other words, for delta modulation, Fs times delta should be at least 280 pi, and delta has been given to us in the question as delta equals 0.1 pi, so we can substitute that for delta. So we will take the delta to the other side of the inequality, so we will have Fs should be at least 280 pi divided by delta. So that would give us Fs. Again, just to distinguish that this Fs is for delta modulation, I'll write this dm in brackets here. Fs for dm. Okay, that should be at least 280, excuse my handwriting, 280 pi divided by 0.1 pi. So the pi and pi will cancel out, so we will get the minimum sampling rate for delta modulation should be at least 280 by 0.1, which is 2800 samples per second. So that's the minimum sampling rate required for delta modulation to avoid slope overload when the input signal is this particular m of t. Okay. Similarly, we will compute the minimum sampling rate for differential pulse code modulation. So for DPCM, the condition that must be satisfied is Fs into L minus 1 times delta should be at least the maximum slope magnitude of the input signal, d by dt of m of t magnitude maximum. So that means Fs L minus 1 delta should be at least the maximum magnitude of the slope is 280 pi, so we'll use that here, 280 pi. Okay, that's for this particular m of t. So now we can write Fs again. I'll write here in brackets DPCM. Okay, DPCM. So the Fs for DPCM should be at least 280 pi by L minus 1 times delta. So Fs for DPCM should be at least 280 pi by L. L is given to us in the question as 16. So 16 minus 1 would be 15 times delta, which is into 0.1 into pi. So when we make this calculation, we will get the minimum sampling rate required for DPCM to avoid slope overload should be at least 280 divided by 1.5, or it's 2800 divided by 15. Okay, so I'm not going to simplify this. Okay, we'll just keep it as 2800 by 15. Compare this with the sampling rate required for delta modulation, which is 2800. Okay, so let me write down. Okay, so that's our solution, or the minimum sampling rate required for DPCM. Compare it with the minimum sampling rate required for delta modulation, which was 2800. So if you see here, delta modulation requires a sampling rate which is higher by a factor of 15, because in DPCM you have 2800 divided by 15. So that means DPCM requires a sampling rate which is smaller by a factor of L-1, which is 16 minus 1, which is 15. So you clearly see that from this example that delta modulation requires a much higher sampling rate in order to avoid slope overload distortion. Okay, and that's the trade-off. Delta modulation had some reduction in complexity as compared to DPCM. In DPCM, we had a predictor block, which was a complex implementation that got replaced in delta modulation by a delay block, which is a much simpler implementation. So we have the advantage in delta modulation where the predictor is implemented as a one sample delay, but the price we pay for that is in order to avoid slope overload in delta modulation, we need a much higher sampling frequency as compared to differential pulse code modulation. Okay, and engineering is all about trade-offs. You never get any advantage in engineering for free. So if you try to reduce the complexity, you're having to pay up in terms of increasing the sampling rate to avoid slope overload in this case. So there's always some trade-off involved when you're developing engineering solutions. Okay, so the sampling rate of delta modulation is higher by a factor of L-1. In this case, it is 16 minus 1. Or conversely, we can say that differential pulse code modulation requires a sampling rate which is smaller by a factor of L-1 as compared to delta modulation. So that's the example to illustrate that the sampling rate to avoid slope overload in delta modulation is higher as compared to the sampling rate required to avoid slope overload in differential pulse code modulation. Okay, so that brings us to the end of the first chapter, and in the rest of this lecture I will be talking about or giving an introduction to the topics of the next chapter, and we'll actually move into the next chapter in the next lecture, but I will give you a brief introduction to what we can expect to see in our second chapter.